Continuing from our previous class where we learnt about sensor readouts, we will look at the various common configurations of sensor readouts present. There are four architectures being highlighted. Now let us look at the commonalities between each of them. Look at the input signal. At the input signal of all the four devices or four configurations, you would see that the sensing capacitance Cs is connected to the reference capacitance Cr, and the top plates of both these devices are connected to each other or they are shorted. At that node, you have the parasitic capacitance present. This parasitic capacitance can represent all the noise and capacitance non-linearities present in the circuit, in the sensor as well as in the circuit going forward. Another commonality that is present in all these signals or all these circuits is an amplifier, and some are in closed loop configuration, some are in the open loop configuration. If you look at the circuit in A, it is the sensor output is given to the amplifier, and the amplified signal is fed to a synchronous demodulator. The other signal that is being modulated with is the pulse input given, which acts like a clock, and this typically clock ensures that you work as a move the frequency to a higher dimension. What do you mean by higher dimension? So for example, when you perform a modulation, we are very familiar with this notation for a modulation, which is also for a mixer that does a modulation here. So here is your amplified capacitance value Cs, and on the input you have the pulsed clock that is being given. So this is a low frequency signal or a DC signal, whereas this is a higher frequency in comparison to the two. So let this be called as F1 and the frequency here be called as F2. So when you modulate the signal, you get two kinds of frequencies, right? You get a summation and a difference of these two. So the summation, the difference will be here, which is F2 minus F1, and the other one is placed on the other side, which is F2 plus F1. Now that you have two frequencies, the frequencies of interest that come out here are F2 plus minus F1, which are these two frequency tones. Now after that, you try and pass it through a low pass filter. So once you pass through a low pass filter, you basically try and remove the higher frequency. So the output that is left here is a component of frequency F2 minus F1. So you have a modulated signal present here, and the voltage output of this modulated frequency can be utilized here. If you notice, this nature is also common across all the circuits. So there is some amount of filtering happening across all these circuits to remove the higher frequency. So hence a low pass filter is utilized. If you look at the waveform B, everything looks similar except that the amplifier now is in a feedback mode. So this is an open loop amplifier, whereas this is a closed loop amplification system. Rest everything is still the same, so there is no difference here. What is the impact of having an open loop versus closed loop? A closed loop is already a filtered equation wherein the amplitude is reduced and maintained a very high bandwidth. So if you are sensing bandwidth is small, then with a very high gain, you can use a low pass filter and bring out the output. Now, what are the difference in using open loop and closed loop? Let us look at the gain response of an open loop versus closed loop. So typically this is the open loop, closed open loop, where there is very high gain and there is lower bandwidth. In closed loop, with some amount of compensation, you have a lower gain but a wider bandwidth. So this is your frequency axis and this is your gain. So in this case we have two frequency ranges. This is F open, this is F closed, and here we have the gain open loop, and this is your gain closed loop, right? Now when you want a very small gain and do not want to saturate your synchronous demodulator, go for the closed loop so that your gain is lesser and you have a wider bandwidth. But here the challenge is the LPF has to have a bandwidth all the way till FC. So this you will need to have a closed loop, and here you will have open loop. So in this case what will happen is the cutoff frequency FC for the open loops will be that open loop and closed loop, that F open is less than F closed. So this is the cutoff frequency of the low pass filter, right? So this is one way of bringing out the capacitance values. Another way, which is more commonly used, is your integrator. So here this is a capacitance multiplier, rather, as explained earlier, this is a charge multiplier. Right? This charge multiplier will be able to bring you the difference in the values. How is that? So the amount of charge that is present here, Q, on this capacitance with a certain voltage V is transferred in the same way, but the V present here is reduced so that the charge goes up. And when the charge goes up, so there is a ratio which is maintained. So your C int over CS value becomes greater than 1. So that value is sent out, and since there are high frequency components present here also, you need a low pass filter to filter them out. Do notice that you have phases phi 1, phi 2 and phi reset. Phi reset is turned on. This is closed before any charge is sent inside, such that whatever is the charge that is present can get discharged through the capacitance into the ground. Let me illustrate that with some more detail here. Here you have the phi reset signal. When you close the phi reset signal, all the charge will pass through this short path, or whatever the charge that is present at the output capacitors here will get discharged to the ground. Once that is discharged, you have a effective zero charge present here, and once the reset signal is turned off, the charge process can begin and it can get transferred to the C int. Once this is placed, there is a C out present here which acts like a capacitive divider which is present at the output. So all the charge that is present here goes to C0, and that C0 will allow it to charge. Now the way you read it out is when phi1 is high or it is closed, the switch gets closed here, so the charge reads through C0 and it gets discharged. When the phi is closed and only phi2 is present, you can read the reference capacitor value. So that way you can get a difference of these two values present on C0 and then read it out. So effectively here the value will be the charge present on C0 is equal to the difference of the capacitance Cs minus Cr minus the parasitic resistance charge. Now this charge is nullified at phi1. So the charge present on this C0 due to Cp is nullified. So this goes away. Effectively the difference between Cs and Cr is captured at this output.